Hello everyone, I'm Snigdha Kakkar and this is my channel AccelerateAICareers. Yesterday we solved a very interesting LeetCode problem unique path. Today we are going to solve an advanced level of unique paths which is Leetcode63 unique paths. It has been an all-time favorite of several companies such as Amazon, Microsoft, Google, Meta. Even Salesforce and Apple have asked them in their last 6 to 12 months in their interviews. So let's look at what this question say. You have been given an m by n grid. It's an integer array. There's a robo initially located here at the top left corner, that is grid 0, 0. And the robo tries to move to the bottom right corner, that is grid m-1, n-1 point. And the robo can take only two directions. It can either go in the right or it can go in the down direction. It cannot go to the left, it cannot go to the up, that is it cannot go backwards, and it cannot take a diagonal direction. An obstacle has been placed in the route, like here a diamond has been shown, that's an obstacle. And the spaces in the grid have been marked either by ones or zeros. So if the obstacle is there, that particular cell will be marked as 1. If the obstacle is not there, it is all clear, then it will be marked as 0. The robo can take only path which does not have any obstacles. If the obstacle is there, the robo cannot go through that cell. You have to return the number of possible unique paths this robo can take to reach to grid m-1, n-1, that is the bottom right corner, from the top left corner. You have to find the total number of unique paths and return it. Let's look at an example here. As shown above, you have been given this grid. It's a 3 by 3 grid, that is your number of rows and number of columns is same. And the output is 2, that is the number of unique paths the robo can take is 2. What are the paths the robo can take? It can either take the right direction, go right, then down and then down. So that's one unique path. Or it can start from down, so it can come here, down, but it cannot take a right here since it's an obstacle here, so it can go down, then it can take a right, and then right. So these are the only two unique paths it can take from grid 0, 0 to grid m-1, n-1 position. This is a simpler example given here, but just for understanding purposes, it's good that you have to understand whenever there's an obstacle, the robo cannot go through that cell. So you have to skip that cell. Now the approach I'm going to demonstrate here will be two. First of all, I'll be demonstrating you a solution using Recursion Depth First Search, where I'll be calculating recursively what are the number of ways the robo can reach from this cell to this cell. What are the number of ways the robo can reach from this cell to this cell. And then I can add these two number of ways to reach from this place to this place to this place. I can add those and get the number of unique paths robo can take from grid 0, 0 to grid m-1, n-1. And I'll be doing it recursively using depth first search. Now, but you would say that that's not a time efficient solution. The time complexity might be exponential. But in that case, I'll be using caching. So I'll not be calculating every time number of unique paths to reach to grid m-1, n-1 from here, then here. I will be saving those particular number of ways in a hash map or in a, in a m by n grid where I can save them so that whenever I come across that cell, I know the number of ways it takes to reach from here to here and I don't have to compute again and again. So that will reduce my time complexity to O of m into n, where m into n is the size of the grid. And space complexity also will be O of m into n because you're using a hash map to store the recursive cache solution. So let's look at that code first, and after that we can dive deep into a more optimum approach where we'll use less memory using dynamic programming. So let's look at the recursion code first, understand its nitty-gritties, and then I'll explain you the dynamic programming approach. So let's start coding here. So this solution, as I mentioned, would be time complexity O of m into n, and the space complexity would be again O of m into n, because you're using a hash map here to save your values. Now I will first calculate m and n because I have not been given them in the initial. So I will initialize m as number of rows and n as number of columns. Okay, that's how I get the number of rows and columns. After that I will initialize my hash map dp, and to initialize the hash map I will first initialize the bottommost position, this grid m-1, n-1 position by 1. Because there is only one way to reach there, right? So I can initialize at least that position by 1. For the rest, I will be computing and saving. Now I can write my recursive function DFS, that is depth first search, and I can pass R comma C. I need not pass other variables like M, N, DP through it, because this function is a sub function of this bigger function, so all the variables are already passed through it. Now I will check if we have crossed the boundaries, that is if the rows have reached M, or the column has reached N, or there is an obstacle. So if there is an obstacle grid, RC will be 1 as given in the question. So in that case, we have to return 0, that there are 0 unique paths from there. If R comma C is already in my hash map, that is it is already cached, in that case I don't need to compute it again, I can just return DP R comma C, so that I don't have to do again the similar calculations. Okay, if none of these cases are true, in that case I have to store R comma C. And how do I store R comma C? I would be using Recursion Depth First Solution. And what do I need to add? I need to add the number of paths it takes just from the bottom cell and the right cell, because there are only two directions you can go. Either you can go towards right or you can go towards bottom. So number of ways from here, number of unique ways from here can be computed by calculating the number of ways just to the right of the cell, from there to the grid m-1, n-1 cell, or the number of unique path it can take from just the bottom cell, from there to grid m-n-1. Whatever are the number of ways from these two cells to reach the bottommost corner, if you add them, those are the number of unique ways you can reach from here to here. That's what I'm doing here. So I'm applying recursion and I'm calculating R plus 1 C, that is R plus 1, that means you're just calculating the bottom one just below, and I'm calculating R C plus 1, that is you are calculating the right one, and then you can return DP R comma C. That's your recursion function, that's completed. And finally, what is the result you want? You want the number of unique paths from grid 0, 0 to reach grid m-1, n-1. So finally you need to return the result from 0, 0, 0 cell. So that's what I'm going to return DFS 0, 0. This is your entire solution. It is not the most optimum solution, but it's a good approach nevertheless. So we should first understand this, and then we will understand the most optimum solution. I will run this first. Name grid is not defined. Okay, so I can just change this name to grid rather than changing everywhere. And I think it works. So it is not bad. It's a good solution. But we can make it even better. But how do we do that? So for that, we will be using dynamic programming. So when we are doing recursively, we start from DFS 0, 0. We enter the loop from there. Then we go to DFS 1, 0 or DFS 0, 1. And then we proceed further until we reach this DFS m-1, n-1. And we recursively fetch these values cached in DP hash map, and then fetch them and add them, and finally we get the result for DFS 0, 0. It's not a worse approach, but there could be a better approach. Instead of going recursively from here and then going here, then going here and finally getting here, we can start bottom up and use dynamic programming to do it. And instead of using a hash map, we can just capture one row and we can replace it in place, because if we see, we just need values to be stored for one row. And we can calculate the next row using this. And after we have computed this row, we don't need this row anymore. We can just use this row to compute this, and so on, howsoever bigger metrics we have. So let me explain it here. Suppose you just initialize your DP metrics. Instead of DP metrics, you initialize just your DP row, and you're capturing only this row, and you initialized by 1. Because there is no other way going here in the bottom, there's only one way, that is towards right, and there's only one way to reach here from here, so we initialize it by 1. Now if you want to compute this cell, you would need the value just bottom to it and the value to the right of it, but there is no value to the right of it. So you just actually need the value to the bottom of it, that is this row, and you can replace it in place because you can use only one row memory. So you can just replace it in place. Instead of this one, you can put this one now, this value. Now you have to compute this. Now you know that there is an obstacle here. So you can update your DP by 1 there, as there is an obstacle. Now you come here, you need to compute this. To compute this, you need this value DP here, and you need this value, that is the value to the right of it and the value to the bottom of it. So you actually just need this row's values and the value you are computing for the current row. So you will say that you need 2 rows actually, but that's not right. You don't need 2 rows because you are essentially using these values to compute these, and you can replace them in place, because as and when you start proceeding here towards the left side, you don't need the right side cells anymore. You have already used them for your computation, so you can use them to replace in place. So let me explain from the scratch. This value has been initialized at 1, rest everything say you initialize by 0. Now this value can be computed just by using this cell, and you can compute it because you can only go right from here. So you can add just value here and add 1 here. Same way this value can be computed just by taking value from the right, because there is nothing to the bottom of it, and this value will be 1. So you just needed this and you have the row saved. Now you come here, you need to compute this value, right? To compute this value, you just need this cell because there is nothing to the right of it. So you just add this value, and instead of getting another row to be stored, you just replace this value with this. Now for this value, you need sum of this and this, but you recognize there's an obstacle here, hence you do not apply that formula, and you see there's an obstacle, so the robo cannot cross from here. You update the DP here value with 0. So you can update this row in place. Instead of 1, you can place 0. Now this value will be sum of this and this, sum of value to the right of it and bottom of it. So it will come out to be 1. Now you don't need the bottommost row values anymore. You have replaced them with the second row values, and you need only those values to compute the top row values. So the top row value in the rightmost column, you can get it just by the cell to the bottom of it, because there is nothing to the right, and that will be 1, right? Now just to the right, the cell value here can be obtained by getting the value from the cell to the right, which you just computed, and the value to the below of it, which is an obstacle, so it's 0, and you get 1 here. Now finally, the place from where robo starts, you can get its unique number of paths by adding the value to the right of it and to the bottom of it, which you have stored in the row currently, right? You don't need 2, 3 rows or metrics for storing everything and getting updates. You just need 1 row essentially, and you get 2 unique paths here. So I hope the dynamic programming approach is clear to you. Now we will start coding it. This solution has time complexity O of m into n, and space complexity as O of n or O of m for that matter, whether you store 1 column or you store 1 row. So we first initialize m and n, which are length of grid and length of grid 0, that is length of row and column of the grid. After that, we initialize our dp, which would be essentially the values in 1 row. And since there are n columns, hence I'm multiplying by n and I'm initializing everything with 0. Now I will initialize my last cell value as I did while explaining the algorithm with 1, because there's only one unique way to reach the bottom. Since I'm going in reversed direction and I'm going reversed in rows and reversed in column, so I will write first for row, for r in reversed range m because there are m rows, and then I'll write for c in reversed range n because I am also traveling in reverse direction in columns, and I'll check if grid C is 1, that is there's an obstacle there. In case there is an obstacle, I will update my dp current cell value by 0, because there is no way the robo can pass through the obstacle, right? As if by second case, when we hit the out of boundary condition, that is so the out of boundary condition cannot be hit in terms of rows because you are initializing the bottommost row and you are initializing it with 0. So you cannot hit that condition, but you can hit the out of boundary condition for columns, because you are essentially computing the value just to the right and to the bottom. So for the column condition, in case c plus 1 is less than n, that is you are within the bounds and you have not hit the boundary. In that case, when you are within the bounds, then your current value would be equal to the value just to the bottom of it. Since you are replacing in place, so the value to the bottom of it is in the dp value currently in this row, and you are actually replacing it with the new value. Hence C here, because it's the same column and you are replacing it after computing. And the value to the right would be C plus 1. So you have handled the out of boundary case here. So it will not go beyond C equal to n minus 1. As soon as it reaches c equal to n minus 1, it will stop computing, and then I can just return. And what do I need to return? dp0, because I need not return the entire row. I just need the 0th cell value, and that's my entire code. This is an easier code. You should practice writing it 1 or 2 times yourself. So it's accepted. Let's sum. Yeah, so you can see how much the solution has improved when compared to our prior solution of recursion, which was somewhere here. So this is so much better, right? Now I will just summarize this solution to you once more. So I first initialized my M and N, that is my rows and column, because I don't want to call length grid and length grid 0 again and again. And then I just initialized one row, which is the bottommost row with zeros, and one cell, that is the last cell, dpn minus 1 by 1, because there is one unique way to reach there. And then I travel in reverse direction for row and reverse direction for column. I check if there is an obstacle. If there is an obstacle, question has given grid RC would be 1, right? So I've checked. If the obstacle is there, I update that particular cell's value by 0, because there is no way robo can cross that cell. Otherwise, I check if the column are in inbounds, that is, I'm not crossing the boundary where there is no more values. So I'm checking if c plus 1 is less than n. Why didn't I check for row? Because I myself initialized rows by 0 here. So there is no question that we will reach out of bounds for row. So I have written else if c plus 1 less than n, and then I compute the value by calculating the value just below this below cell, that is the same column but a row below, and the cell just to the right of it, that is c plus 1, that is the next column. Now you must be wondering why I'm updating the same column here and adding the same column value here, because I'm replacing the dp values in place, and I'm not using a matrix to store the values, I'm using just a row to store the values. So currently in my current row C column, whatever the value is there is the old row value, and I'm replacing it with the new row value by adding the old row value, that is the below cell, and the right value, okay? And then finally I return dp0 because I just need the 0, 0 grid value. I hope you understand the solution. If you have any doubts, mention in the comments. I would be happy to explain it in detail. Subscribe to my channel if you like my way of solving problems to get your notifications for your daily LeetCode challenge. Let me know if you have a better solution. I would love to learn from you. Thank you.